Okay, so we finished complex numbers. Now we're going to do this video. I'm going to cover domain inverse composition. I'm going to try and do this a little bit faster, so hopefully it won't be more than 15-20 minutes. Okay, so domain. And an x value is in the domain of a function. If its corresponding y value is real and defined. Okay, what this means is that we have a limited number of possibilities. Okay, so the first possibility is just f of x equals some expression like 3x plus 2. Okay, we have, so when we say real, okay, the only thing that would make something not real is a radical. And the only thing that would, square root of a negative number. And the only thing that would make something undefined is if we have a 0 in a denominator. So here there are no radicals and no denominators. So our domain is negative infinity to infinity. And we would write x equals, because we're talking about a domain, and it's negative infinity to infinity because there are no radicals and no denominators. Okay, that means that there are no restrictions. Okay, let's take the second case. So the second case is if we have a square root. So let's take square root of 2x minus 4. So there's a radical. Our radical has to be greater than or equal to 0. So we're going to set up an inequality. 2x minus 4 is greater than or equal to 0. In other words, anytime that we see a radical, what's under the radical has to be greater than or equal to 0. Square root of 0 is 0. That's fine. But the square root of a negative number is not real, and we need it to be real. So 2x minus 4 is greater than or equal to 0. That means that we're going to add 4 to both sides. That says that 2x is greater than or equal to 4. Divide both sides by 2. So x is greater than or equal to 2. The way that we would do that in interval notation, there's a bracket because there's an equal sign. And we would say it goes from 2 to infinity. And we would close it with a parenthesis. Infinity always gives us a parenthesis. And we have, in standard notation, you could write it as x such that, so it's any x value, except x has to be greater than or equal to 2. So here we use braces. So these are the two different ways that we could write the domain. You don't have to write both. You can choose. The third possibility is if you have a denominator. So no radical, but you have a denominator. So for example, you have 7x minus 1 over negative 3x plus 9. So in this case, your denominator can't be equal to 0. Okay, so your inequality is negative 3x plus 9 is not equal to 0. And we solve that. We subtract 9 from both sides. We solve it just like an equation. Negative 3x is not equal to negative 9. Divide both sides by negative 3. Now you don't have to do anything with this inequality. If this were an inequality that had a greater than or less than sign, then you would have had to switch the inequality, but not equals. There's nothing that you could do. So here this is saying x is not equal to 3. So we want to write that in interval notation. We would say x equals, and we would say we go from negative infinity to 3. 3 is not included. We jump over 3. That's what this union is. That U says we're jumping over the 3. Notice we have parentheses here, so it's not including the 3. And then we go from 3 to infinity. Or, and this is why I kind of like standard notation for ones like this better, we're saying it's any x except x can equal 3. Okay, then we have the fourth possibility. So the fourth possibility is where we have both. We have a denominator and a radical. And in this case, our radical is in the denominator. So we have 2x plus 9 over the square root of, let's say, 4x minus 12. So our radical has to be greater than or equal to 0. Our denominator can't be 0. So what we're doing is we're saying 4x minus 12 has to be greater than or equal to 0, and 4x minus 12 can't be 0. So we can combine this. Why solve two inequalities when we just have one? We could say, okay, so 4x minus 12 is greater than 0. So you don't have to write both of these. I wrote them here, but you don't have to write both of them. You can just say 4x minus 12 is greater than 0, because we're saying it's got to be greater than or equal to because of the radical, but it can't actually be equal to because it's in a denominator. So therefore, it can only be greater. Notice the numerator is irrelevant. The numerator can be positive, negative, 0. If we have a 0 in the numerator, the fraction is just 0, so it's not a problem. We solve this, add 12 to both sides. 4x is greater than 12. Divide both sides by 4. We have x is greater than 3. And notice there's no equal sign. So in interval notation, we would have a parenthesis, 3 to infinity. And in standard notation, it would be x such that x is greater than 3. Okay. And then we have one last situation, and the last situation is if we have both, but this time the radical is in the numerator. So we have f of x is equal to, let's say, the square root of, let's make this negative 2x plus 10 over, let's make it, I want to try and make it easy numbers. So let's make it 3x minus 9. Okay. So our radical has to be greater than or equal to 0. Our denominator can't be 0. And when I say radical, I really mean radicand. I just know that we haven't talked about it that much. So what we're saying is what's under the radical has to be greater than or equal to 0. Okay. So we have negative 2x plus 10 has to be greater than or equal to 0. It can be 0 because it's in the numerator. This is the only time that you have two restrictions. So we're going to solve this. We subtract 10 from both sides. We have negative 2x greater than or equal to negative 10. We divide by negative 2 on both sides. And this is a case where the sign flips. So x is less than or equal to 5. So the sign flipped here because we were dividing by a negative number. So then let's take the 3x minus 1, the 3x minus 9 and solve. So we have plus 9. 3x is not equal to 9. Divide both sides by 3. X is not equal to 3. So we want to check for redundancy. So x is less than or equal to 5. 3 is less than or equal to 5. So x not equal to 3 is not redundant. We have to include both. Okay, so what this means is in interval notation, and again, this is why we prefer standard notation for this. We're saying that we're going from negative infinity to 3. And then we're skipping over 3. And we're going to 5. And we have a bracket here because 5 is included. And in standard notation, the nice part is we don't have to worry about what we're skipping over. We're just saying x such that x is less than or equal to 5, comma, x is not equal to 3. If it had been redundant, we would leave out the x not equal to 3 here. Okay. If you're being redundant and you put it in there, then you will get points off. So you have to check for redundancy. Okay. And there is no special order to these. You could put either one first. So that's domain. Let's look at composition. So composition says the output of one function becomes the input of another. Okay, this is where we talked about things like doing laundry. Okay, you put your dirty clothes into the washer. What comes out of the washer is wet, clean clothes, and those wet, clean clothes go into the dryer. So your washer and your dryer are your two functions. And there are two ways to write this. So we could write it as f of g. So we can rewrite it as s. Then we can also change the order, say g of as g f. So if we take two functions, f of x equals 2x4, f of x equals x plus 1 x, then what we're saying is that g of x represents in f of x. No multiplication, okay? We're not like it looks like multiplication. This is saying our input of f now x is saying every time that you see an x in f, it's now going to be g of x. So there was an x, so we're replacing it with x squared plus 1. And then we have minus 4. Okay. So we had 2 times x squared plus 4. I'd have to simplify that. If you distribute, you get 2x minus 4 or 2x squared minus 2. I'm not going to do it in this review for the most part. Okay. Now, if we change this and we did g of x, of x